As our first step into studying intersections, we'll consider the most basic situation, two lines in two dimensions. While basic, we will start to see structures and procedures that will remain present in more complex examples. A line in two dimensions can be defined by two essential properties: a point it passes through, which I'll call the base point, and a vector that gives the direction of the line. Given the base point x0 and the direction vector v, we can represent all points on a line in the form x of t equals x0 plus t times v. Notice that I'm abusing notation by treating points as vectors here. This means given any number t, we can find a point on the line by plugging in t to the expression x0 plus t times v and computing it. If we were to theoretically plug in all possible values of t and plot them, we'd end up with a plot of all the points on the line. This expression is called a parametrization of the line, since we are expressing the line via the parameter t. For example, for the line x of t equals the vector 1, negative 2 plus t times the vector 3, 1, taking t equal to 0 gives us the output 1, negative 2, which is the base point for this parameterization of the line. If we take t equals 1, then we get the output 4, negative 1, another point on the line. If we take t equals negative 1/2, then we get negative 1/2, negative 5/2, yet another point on the line. Note that a given line has infinitely many base points, since we can pick any point on the line to be the base point. And it has infinitely many direction vectors, since we can multiply any direction vector by a positive scalar and it will still point in the same direction. We could also multiply the direction vector by a negative number, and the same set of points will be parameterized, just starting from the opposite direction. We can't multiply the direction vector by 0 though, or else we'll collapse the line to a point. You may have seen lines written in the form y equals mx plus b, where b and m are numbers. This equation encodes both a base point and a direction. B is the y-intercept, the y-coordinate of the point at which the line intersects the y-axis. This gives the base point 0, b. M is the slope of the line, which can be translated into a direction vector of the form 1m. For every unit of movement in the x direction, there are m units of movement in the y direction. This equation for representing a line isn't perfect, however, since we do not have the ability to define vertical lines. A more general form of equation for representing a line is ax plus by equals k, where a, b, and k are numbers, and at least one of a or b is non-zero. To reconstruct a base point from this equation, there are two cases. Assuming b is not 0, you can set x to be any number. I'll take it to be 0 for this example, which becomes the x-coordinate of the base point. Then you can solve for y to find the y-coordinate of the base point. Having taken x equals 0, this becomes y equals k over b. So a base point for the line is 0, k over b. On the other hand, if b does equal 0, then a will not be 0. Let y equal 0 in this case. Solving for x gives us x equals k over a. So a base point will be k over a, 0. So for this example here, two possible base points would be 0, 2, and 3, 0. Now let's think about the direction vector. If we write down any 2 points on the line, then the vector connecting the points will be a direction vector for the line. In this example, we've already written down 2 points on the line, but for a general case, how would we find the direction vector? Let's start with a very particular case, when the constant term k equals 0. Here the equation reduces to just ax plus by equals 0, and notice that this line passes through the origin, since the base point for this formula is 0, 0. If we draw the vector from the origin to another point x, y on the line, then the corresponding vector xy will be a direction vector for the line. Now here's a neat algebraic trick. Rewrite the left-hand side of this equation as a dot product of 2 vectors. Ax plus by becomes the vector ab dotted with the vector xy. Now what does this equation mean? It means that the point x, y is on this line if and only if the vector xy, a direction vector for the line, is orthogonal to the vector AB. This means we can find a direction vector for this line by picking some vector orthogonal to AB. One good way to do that, in 2 dimensions at least, is to just swap the coordinates in the vectors and negate one. So picking b, negative a, would give us a direction vector for this line. So for the case of this pink line, a direction vector would be 3, negative 2. Now what if k doesn't equal 0? What changing k does is it shifts the line off of the origin. It doesn't actually change the direction of the line at all. So a direction vector for ax plus by equals k, regardless of what k is, will still be b, negative a. So both the pink and green lines will have 3, negative 2 as direction vectors. One reason this way of looking at the equation ax plus by equals k is important is that it gives us an implicit description of the line as a single equation. In particular, as the set of points such that a particular vector dotted with those coordinates x and y equals a given number k. This form also lets us quickly read off the coordinates for a vector that is orthogonal to the line, also called a normal vector to the line. In this case, a normal vector for the line 2x plus 3y equals 6 will be 2, 3, since any vector that is parallel to this line will be orthogonal to the vector 2, 3. We will explore this concept further when we look at planes in 3 dimensions, as well as when we start using linear algebra to solve systems of equations.